College Algebra, Module 6, Topic 6.1, Transformations of Graphs. There are a few basic graphs of functions you need to know. They are the identity function, the square function, the square root function, the cubing function, and the absolute value function. And we're going to talk about each of these in greater detail. Linear functions have straight line graphs. Quadratic functions have parabola-shaped graphs, which were these kind opening upward or those opening downward. Cubing functions have S-shaped graphs, meaning they go up like this or they might go down like this. Absolute value functions have V-shaped graphs like that. Square root functions have a different shape. They are shaped sort of like that. Sort of imagine half of a parabola lying on its side. So let's talk about the identity function first. The identity function says f of x is equal to x. This first picture right here, f of x is equal to x, if you'll think back to your linear function, f of x equals ax plus b, the slope is the number in front of our x, so for our identity function the slope is 1. The number out at the end is the y-intercept, so for this identity function the y-intercept is 0. Therefore 0, 0 is a point on the graph. The slope is 1, which means every time we rise 1, we run 1, we're back on the graph. Rise 1, run 1, we're back on the graph. So that's where that comes from. On your calculator, it would look something like this middle graph. And if you look at a table, what it says is that the y value is the same as whatever the x value is. Therefore, it's the identity. Now, f of x is equal to x is increasing because it goes up from left to right, and it's continuous on its entire domain, which means you never have to pick up your pencil when you're drawing it. Again, the domain is from negative infinity to positive infinity because it doesn't matter what number you plug in for x, the y value is always going to be the same thing. The next type of function is called the squaring function, which we know as quadratic type. F of x is equal to x squared. The first picture talks about f of x equals x squared, and if we just plug some points, if x is 0, squared would be 0. If x is 1, 1 squared is 1. Also negative 1 squared would be 1. And the same thing for if x is 2, we get 4. If x is negative 2, we get 4 as well. Now the second picture is x squared on your calculator, and the third table is what our calculator would look like if we typed in y equals x squared. Now, f of x equals x squared is continuous on its entire domain, meaning that we can pick whatever x we want and square it and get an answer. Continuous meaning that we do not have to pick up our pencil, we can draw the picture in one big mark. Now this function is increasing on the interval from 0 to infinity, and it's decreasing on the interval from negative infinity to 0, meaning starting at 0 the values go up, and before we get to 0 the values go down. The graph again is called a parabola, and the point where the graph changes from decreasing to increasing is called the vertex of the graph. The next function is called the cubing function, and it's of the form f of x is equal to x to the third power. And I said earlier that the cubing function is sort of an S-shaped graph. It's sort of like a parabola, whereas a parabola, when you square it, is always positive. On the cube function, instead of coming back up to positive, it goes back down to the negative values. the third picture shows the table that we used in order to get the first and the second graph. F of x equals x to the third increases and is continuous on its entire domain of negative infinity to positive infinity. Again, that means that the domain is all real numbers. We can pick any number and cube it and still get a real number answer. The point at which the graph changes from opening downward to opening upward is called an inflection point. That would be this point right here. The fourth function is the absolute value function. F of x is equal to the absolute value of x. Now the definition of absolute value as a function says f of x is equal to x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0. And I know this may be a little bit confusing because at one point you learned that the absolute value is never negative. Well, let me clarify this for you real quick. If you pick any number that's greater than or equal to 0, let's say we pick 4. F of 4 means the absolute value of 4, and the function says that the absolute value is just that number, so it would be 4. If we picked x as negative 3, then f of negative 3 means the absolute value of negative 3, and what our function says is it's the opposite of whatever that x value is. So in this case it would be the opposite of negative 3, which is positive 3. So if you see this function notation for absolute value, just know that this is how we have to set it up so that we guarantee our answer is never negative. Now this first graph is a picture of what the absolute value looks like. Notice f of x is equal to x. That's sort of like the identity function that goes right through here. Well, absolute value is never negative, so what happens is it takes these values down here that were negative and it changes them to a positive, which puts them back up there. So this is why we always refer to absolute value functions as being a V-shaped function. Again, the second picture is what the calculator would show, and the third picture is the table that we get when we type in the function the absolute value of x. Now, f of x equals the absolute value of x decreases on the interval from negative infinity to 0, meaning it decreases up until we hit x is 0, and then from 0 forward it increases, which means it goes up. And again, absolute value is continuous on the entire domain. And then the last basic type of function you need to know is the square root function. F of x is equal to the square root of x. Now, as I told you earlier, this function looks like half of a parabola lying on its side. If you come over here and look in the table of values, the square root of 0 is 0. The square root of 1 is 1. So square root of 0 is right here. If x is 1, y is 1 here. And then it sort of flattens out a little bit. Then we sort of jump around a little bit. The square root of 4 is 2. The square root of 9 is 3. So notice it's going to get very flat, or it's not going to get very high very quickly. So that's what our square root function looks like. Now the square root function, square root of x, can also be rewritten as x to the 1/2 power. This function increases and is continuous on its entire domain from 0 to infinity. Note, this domain is not all real numbers because we can only start taking square root at 0. We can't take the square root of negative numbers, therefore there is no graph to the left of 0. Okay, so now we're going to talk about transformations, and we're going to use those 5 basic graphs to graph more complicated functions. So for the first example, to sketch the graph of f of x equals x, we realize this is an identity function. The identity function says if x is 0, y is 0, if x is 1, y is 1, if x is 2, y is 2, and f of x goes right down through all of those 3 points. Okay, now we're going to sketch the graph of f of x equals x minus 3 using a big table. So in the original problem, let's choose 0, 1, and 2. In the second column, I'm going to use the table that we just did earlier. If x is 0, f of x is 0. If x is 1, f of x is 1. If x is 2, f of x is 2, because f of x was whatever x was. Now on this one, we're going to plug it into the new function. Well, if we plug in 0, we get 0 minus 3, which is negative 3. If we plug in 1, we get 1 minus 3, which is negative 2. And if we plug in 2, we get 2 minus 3, which is negative 1. Okay, now if we graph these on the same graph, if x is 0, y is negative 3. Well, that's this ordered pair right down here. If x is 1, y is negative 2, which is this point right here. If x is 2, y would be negative 1, which is this point right here. So now if we drew the line that passes through those points, notice it looks just like our identity function. The only difference is every point was shifted down 3 units. So that's how we're going to use these transformations to change one of our 5 basic graphs to the new function. So we could look at this and go, well, if f of x is x minus 3, what that means is we are shifting the original graph down 3 places. So objective 1 is vertical shifts, is if c is greater than 0, the graph of f of x plus c is obtained by shifting the graph of f of x upwards c units, and the graph of f of x minus c is obtained by shifting the graph of f of x downwards c units. So in our picture, this first line right here is our f of x line. F of x plus c, if you'll think about it, by adding c to the end of the number, that means we're just adding c onto the y values, which means that we're shifting it up c units. And then the same thing down here. If this is our original function, y equals f of x, and we're doing minus c, then what that means is we're shifting the same graph down c units. So for example, write the equation for a function that has the shape of y equals x squared, but is shifted down 2 units. Well, f of x is equal to x squared. To shift it down 2 units, all we're going to do is subtract 2. To graph that, well, we're going to go back and realize that f of x equals x squared looks like this. So if we drop all the points down 2, then f of x equals x squared minus 2 is the same graph, just shifted down 2 units. Objective 2 is horizontal shifts. And what this says is, if c is greater than 0, the graph of f of x plus c is obtained by shifting the graph of f of x left c units. Now this one's a little bit tricky, but if the x plus c is inside parentheses, then you use the opposite of c, which means instead of moving it over to the right c places, we're going to move it back c places. So if this black line is the graph of f of x, then f of x plus c means we're moving the graph to the left c units. The same thing for the graph of f of x minus c. That is obtained by shifting the graph to the right c units. Okay, let's do an example of these. Write the equation for a function that has the shape of y equals x to the third, but it is shifted to the left 4 units. So a horizontal shift goes in the parentheses with the x. So for this one, it's going to be f of x equals x plus 4 to the third. Because again, if we're going to the left, even though it's in the negative direction, we have to write plus 4 to get it to go to the other side. Okay, let's do some examples. We're going to do f of x plus c, and f of x plus c. So if our first function is f of x is equal to x, this is our basic graph that goes right through the origin with a slope of 1. Now the second one, to do the transformation on it, because it's on the end, that means we're going to shift it down, and we're going to go down 1 unit, and then we're still going to put our same line in there that goes up 1 over 1, up 1 over 1, and that graph is going to look just like the first one, but it's going to be shifted down 1. Now the third one, f of x plus 4, well, if our original function was x, then we substitute in x plus 4, so we get x plus 4. This one looks a little tricky because if it's x plus 4 here, that means we're going back 4 to put our point. So we're going to take this same picture that we had here and move all of our points back 4. Well, now if our slope is 1, we go up 1 over 1, up 1 over 1. What happens is we get that same little line. Now this is a little bit tricky because this also looks like, well, it's the same function x plus 4. Well, if we look at that and we extended that one on out, that's the same thing. So for this one, just the way it's written, it's a little tricky. It could be x function shifted back 4, or it could be the x function shifted up 4. Either way, we're going to go back 4 here and up 4 here. Most of them aren't going to be this confusing. Let's do another example. If we do f of x is equal to x squared. Okay, our typical parabola is this little shape right here. X squared plus 2, because we're adding it to the end, that means we're going to go up 2. So this graph, instead of doing a vertex at 0, 0, we're going to shift it up 2, and then we're going to draw in our parabola going up like that. Notice it's the same picture, we're just shifting it up 2. Now this third one, if it's x plus c in parentheses, that tells you it's a horizontal shift. If it's a plus c in parentheses, it goes to the left. If it's an x minus c in parentheses, it goes to the right. So this one is x minus 3, which means the shift is going to go 3 places to the right. So instead of our vertex being at 0, 0, we're going to shift it to the right, and then we're going to put in the parabola. Okay, another example. Explain how transformations can be used to find the graph of y equals x plus 5 squared minus 3 based on the graph y equals x squared. Okay, I always like to start out with our point of reference, which is going to be our parabola y equals x squared. Now the x plus 5, if it's in parentheses, that's a horizontal shift, and it's always the opposite sign, so this one is going to be back 5. The number on the end tells us the vertical shift, which is going to go exactly with whatever the sign is. So for this picture, we're going to do our parabola. Instead of having a vertex of 0, 0, we are going to go back 5 and down 3. This is where our vertex is, back 5, down 3, and then we're going to draw in our parabola from there. Describe how the graph of y equals the absolute value of x plus 2 minus 6 would be obtained by translating the graph of f of x equals the absolute value of x. Well, your red line is your absolute value of x. The x plus 2 inside the bars, remember, change the sign, so that means it's going back 2 places. The number on the end is the vertical shift, which means we're going to go down 6. So from this point right here, we're going to go back 2, down 6. 1, 2, 3, 4, 5, 6. There's our vertex. If we took this point, back 2, down 6. There's that point. If we took this point, back 2, down 6. So basically the whole graph is just shifted back 2, down 6, and that gives us the new graph of the absolute value of x plus 2 minus 6 in green. Remember that all of these transformations can be observed also on the graphing calculator. Enter the original function as y1 and the new function as y2. You should be able to recognize the difference. For example, let's compare the graphs of f of x equals the square root of x and f of x equals the square root of x plus 2. So when we go to y equals, the first function is going to be the square root of x. Then the second function is going to be the square roots. We're going to go second square root of x plus 2. Now remember, whenever we want to talk about comparing graphs, we can go over here to the left of y2, press enter, and that's going to give us a little bit darker line. So when we graph these, this first line is y equals the square root of x, and then the second graph is the square root of x plus 2. Notice it was the same graph, it was just shifted 2 places back to the left. Now, I didn't ask you this, but what if I asked you for the f of x is equal to the square root of x plus 2? Now notice on this one we're going to go to y equals the square root of x only in parentheses plus 2. Now what do we think is going to happen? Well, the plus 2 means we're going to shift it up. So when we graph it, there's our x, square root of x. There's our square root of x plus 2. And then there's our square root of x plus 2. So, summary of transformations so far. We just saw how adding or subtracting a constant to a function can cause a shift, either vertically or horizontally in the graph. Now we will see how multiplying a function by a constant will affect the graph of the original function. We will refer to these changes as stretching, shrinking, and reflections. Objective 3 is vertical stretching. If c is greater than 1, the graph of y equals c times f of x is obtained by vertically stretching the graph of y equals f of x by a factor of c. What that means is the larger the value of c, the greater the stretch. Okay, so for this problem, y equals f of x was the black line. When we multiplied that by c, you notice how it got taller to start with and it got lower to end with? So what that means is for the original function, we had the order pair -1, 0, 0, 1, 1, 0, 2, -2, and 3, 0. Well, if our new function is cf of x, or c times the y value, in this one it looks like that c is 2, so that would be 2y. So x equals -1 would be 2 times 0, or 0. If x is 0, multiply that y value by 2. If x is 1, multiply that value by 2. If x is 2, multiply that value by 2. And if x is 3, multiply that value by 2. Notice that just increased the range of our y values. Now, objective 4 is vertical shrinking. And what that says is if c is between 0 and 1, meaning if c is a fraction value, then the graph of y equals c f of x is obtained by vertically shrinking the graph of y equals f of x by a factor of c. The smaller the value of c, the greater the shrink. So in this case, same thing, we started out with the black function y equals f of x. If c was 1/2, which is what it looks like, because whatever the y values were are now cut in half. Okay, and then objective 5 is reflecting across the x-axis. For a function y equals f of x, the graph of y equals negative f of x is a reflection of the graph across the x-axis. So for this problem, y equals f of x was the green line. Now what that means is, for this first point, if we were up this many units, then for a reflection, then we go down the same number of units. For the second point, if we went up a units, the reflection means we're going to go down a units, and so forth. So whatever we did up at the top, now we're doing down at the bottom. And what this looks like is y equals the negative of f of x. So objective 6 is combining all the transformations so far. Describe how the graph of y equals negative 3 times x minus 4 squared plus 5 can be obtained by transforming the graph of y equals x squared. Now think about it. If I asked you to graph this by hand, you would probably think, oh no. But because we can transform x squared, it's not as bad as it looks. So for this problem, first thing we're going to notice, in parentheses we had x minus 4. That means we are going to shift it 4 units to the right. Okay, so 4 units that way. The second thing we're going to look at is because there is a number out front that's being multiplied, that means we are going to stretch it by a factor of 3. The next thing we're going to look at is the negative out in front. The negative out front means we're going to reflect it across the x-axis. And then the last thing we're going to look at is the positive 5 means we're going to shift it 5 units up. Now I've got this on the next page, so let's go through and look at it in pieces. Our equation was y equals negative 3 times x minus 4 squared plus 5. So we're going to start out. Now remember the x squared is right here. Went through 0, 0, 1, 1, negative 1, 1. So it looked like this. So the first thing we're going to do is we're going to shift it to the right 4 places. So 1, 2, 3, 4. So there's our vertex. There's our other additional points of reference. The second thing we're going to do is, because the factor of 3 is, we are going to multiply everything by 3. Well, that was 0, so that's going to stay the same. This was up 1, so now what we're going to do is we're going to go up 3 on both sides of that vertex. The third thing we're going to do is we're going to look, and because it's a negative, that means it's a reflection. So now we've got our point of reference here, but instead of going up 3 on both sides, we're going to go down 3 on both sides. And then lastly, the number 4, the point on the end, because it's a plus 5, we are going to take this reference point, 1, 2, 3, 4, 5, and that's where our new vertex is going to be. So we've got our new vertex here. We still have our points that are 3 units below that, and that's how we would graph the function y equals -3 times x minus 4 squared plus 5. Now, as a caution, the order in which transformations are made is important. If they are made in a different order, a different equation can result. For example, the graph of y equals 2 times the absolute value of x plus 3 is obtained by first stretching the graph of absolute value of x by a factor of 2 and then translating up 3 units. Now the graph of y equals 2 times the absolute value of x plus 3 is obtained by first translating y equals the absolute value of x horizontally 3 places back and then stretching it by a factor of 2. Okay, you are now ready to do the homework for Module 6, Topic 6.1 in my math lab.